This video is on ranking, boiling, and melting points, and then on some unique properties of water. So, some things to keep in mind when ranking, melting, and boiling points is that the stronger the intermolecular forces are, the higher the melting or boiling points will be. So, we want to rank the following in terms of boiling point, with a 1 being the highest boiling point. So it might be worth reviewing strength of our forces first. Our number one strongest force will be our ionic bonds. And then with our covalent bonds, we are going to look for things that can hydrogen bond next. We're going to look for things with dipole forces. And then we're going to be left with those that only have dispersion forces. I'm just going to leave it like that for dispersion forces. Now, when there's ties, we can look at the mass of substances. So the first thing we might want to look at in these 5, are there any that have ionic bonds? Because those are full-on pluses and minuses, really strong, right? Because these have an actual plus and minus charge that are always going to be attracted to each other. If you notice, MgCl2 starts with a metal. That's ionic. That's going to be number 1 because that is ionic. Okay, then let's look for anything that has a hydrogen bond. Now, it's not just everything with hydrogen in it. Let's look a little carefully. CH4, the C to H bond is not polar, so that's not even dipole. We can look at CH3F. Now, because the H and F are written together, you might think that that has hydrogen bonding, but the C is bonded to 3 H's and then the F, because, F's halogens, like fluorine, chlorine, bromine, they bond like hydrogen, only 1 bond each. So we don't have the H directly bonded to the F, so that's not hydrogen bonding. But water is hydrogen bonding. We know that the O bonds to the H's in water. And so that is hydrogen bonding, so that will be your number 2. Okay, now CF4 and CH4, they're both symmetric, so they're not polar. So all they have are dispersion forces. Let's leave those. Let's check CH3F. Well, the C to H bond is not polar because you've got 2.5 minus hydrogens, a 2.1. That's only a 0.4 difference. So if you've got a 0.4 difference, that's non-polar. But the C to F bond is going to be polar. And so you can go ahead and check that. But fluorine is a 4, and carbon is a 2.5. So you've got 4 minus 2.5. You've got a 1.5 for an electronegativity difference. This is a really polar bond. So because of that, you are going to have dipole forces. So, maybe I need to label this one with H bond, and this one's going to be dipole. So this is our number 3. CH3F is our number 3. And then we've got CF4 and CH4. Now these are going to be tied. They're dispersion forces only. That's a pretty weak force. We're down to size. Fluorine's got more mass, more electrons, so that's going to be 4. And our CH4 is going to be 5, our lowest boiling point. Okay, so first, ionic compounds had the strongest attractions, and they had really high melting and boiling points. So the ionic compounds, they always win, like we had magnesium chloride, winner. Then we determined the intermolecular forces present in all of the other covalent compounds. More IMFs, like hydrogen bonding, that wins. Then dipole, lastly comes dispersion. If molecules only have dispersion forces, the one with the higher mass, more electrons to do more bunching up for dispersion forces, that one will have the higher melting and boiling point, and that one will win. Okay, Let's try these examples. We're going to circle the compound with the higher melting point and explain. Okay, so NH3 or CO2. Well, nothing's ionic here, but NH3, that can hydrogen bond. So that is for sure going to win. CO2 is not even polar. That's nonpolar. That's only got dispersion forces. Okay, CH4, very similar, just dispersion forces. But hey, that's what CO2 has as well. So then, if they're both dispersion, it is going to come down to mass, and CO2 is going to be higher mass. And again, because they were both dispersion, we really needed that sort of tiebreaker to, help us figure that one out. Higher mass, more electrons, do more bunching up. That will give you the higher melting and boiling point. Now we've got H2O versus HCN. Well, H2O can hydrogen bond. There's no hydrogen bonding when H bonds to C and then C bonds to N. There's no bond between the N and the H, so no hydrogen bonding there. So H2O is going to win with the hydrogen bonding ability. I'm going to put my air quotes back in there because remember, it's not a bond at all. H2O or NaCl, well, sodium chloride, of course. Ionics always win. They have full-on pluses attracted to full-on negatives. That's how I think of it. Okay, now, one last really important but big and cool concept we want to cover is how unique water can be. Water is so important to us, right? It's absolutely vital for our everyday life. And we, have it as a liquid at room temperature. That's really pretty cool. For its molar mass, most things that were that mass, or similar mass, like let's take CO2, NH3, these are gases at room temperature. So the fact that water is a liquid at room temperature and we can drink it and it dissolves so many ions, that is really cool. And it has a relatively high boiling point that keeps it in a liquid at room temperature because of its strong hydrogen bonds. Another really unique thing, okay, so this being a liquid at room temperature and this relatively high boiling point, that is all about its ability to hydrogen bond. Because it hydrogen bonds, that really allows it to be so unique. It also expands as it freezes. Now, most substances, they'll contract as they freeze. Look at the paraffin wax here. It's contracting as it freezes, as shown in these images of the molecules compacting and getting more dense and sinking. That's what most solids do. But what's really weird about water is that it actually expands as it freezes. So it's less dense in the solid ice form than it is in liquid water. And that's, again, due to these hydrogen bonds. Hydrogen bonds really help the hydrogen of one water molecule want to line up to the oxygen of the next. And then it makes these cool little hexagons. And these hexagons are what snowflakes are based off of. The fact that it can make these little hexagons at the molecular level is the start of every single snowflake. But anyway, it also leads to a lot of empty space in the center of that hexagon, making solid water, ice, less dense than liquid water. That is so phenomenal. I mean, the fact that ice cubes float on liquid water, we don't really think of as that cool because we just kind of get to drink it every day, but it's really pretty phenomenal. And it's really vital for life. If you think about it, this is the whole reason that ice floats on lakes in the winter, and you would expect it to sink to the bottom. Well, that would kill fish if the ice were sinking to the bottom. Eventually, the whole lake would freeze, but it doesn't. So here's what's weird. As water molecules slow down and cool off, they do get denser and denser and denser. And water is densest at 4 degrees Celsius. So that is its densest point as it's cooling. So it's going to sink in the lake when it is 4 degrees to the bottom. But after 4 degrees, as the water cools to 3 or to 2 degrees, it actually starts to expand and make those hexagons. And so any colder than 4 degrees and some expansion is occurring, and that water will float on the densest 4-degree water. And so here you can imagine hexagons are starting to form, starting to form, starting to form. They've formed in that ice layer. And so the densest water gets trapped at the bottom of lakes at 4 degrees, and that keeps fish alive all winter. And so without that interesting property where water is densest at 4 degrees and actually less dense in its solid form so it can float, due to hydrogen bonding, life as we know it would be really, really different without hydrogen bonding and without water's ability to do this expansion upon freezing. And so it's this being densest at 4 degrees that leads to nutrient cycling in the spring too. Nutrient cycling throughout the year, and the lake is, due to these temperature factors. And so without getting into too many more details, let's just suffice it to say that water is pretty cool, really, because it can hydrogen bond.